Hello there. This is Sir DV again to discuss to you some concepts on slope deflection method. So this is a continuation of our topic from the embrace frame concepts using slope deflection method, and I already explained to you that the basic principles of the slope deflection method. So the problem here is now applied for gravity loads, and I'm using again the MathCAD tool for my computation. So we are asked to find the moments of the frame considering the gravity loads given using a slope deflection procedure. So to give you a recall on what we did last time, we actually defined the formula, the general slope deflection equation, as the basis for your solution. And I also uh, gave you this figure here to represent the effect of end rotation uh, and the effect of joint translation. Okay. So the effect of the rotation and translation will give us angles theta I and theta j, where in theta I represents your rotation at the near end, and theta j represents your rotation at the far end. Okay, so the subscript mij here refers to the direction in which your member is actually directed towards the positive local axis. So the effect of rotation at the near end node is actually twice the effect of the rotation at the j end node. So we can see here in this equation that this value in the expression, the first two expression inside the parentheses represents the effect of rotation, and the value of the third expression, which is a negative expression, represents the effect of your joint translation. Okay, so the sign convention is positive, since if you consider this curvature, okay, upon which your moment rotation is counterclockwise, directed counterclockwise, so the moments are now negative moments, while the rotation are positive rotations. Okay, so here the moments are negative moments, while the rotation is a negative rotation. Okay, so these are positive rotations. That's why you can see here a plus plus minus sign here. So when we're talking of rotations here, we are talking of the chord rotation, upon which we connect the two ends of the deformed configuration of your member to represent a chord. And since this is oppositely directed with that of the rotation on the at the ends, this is a negative in terms of sign. So the 3 here simply refers to the uh, derived equation considering a delta deformation, wherein your moment due to that displacement is simply equal to 6ei over L times your delta. Okay, where your 6ei here represents the 6 times 2 here. This is a 6ei. while the formula here is a 4EI over L. So this is L, I think L cubed, and the moment due to the rotation is a 4EI, okay, theta I all over L squared, and a 2EI theta J over L squared. So if we are referring here at Mij and Mij, okay? So the influence of these three values for your moments will actually be summed up into this value here. So for simplicity, we can make use of a relative stiffness to Ek to be a constant equivalent to 1 if we are to use relative stiffnesses rather than absolute stiffnesses. So we can say that the members have the same relative stiffnesses or have the same values of stiffnesses, so that the relative stiffness is simply equivalent to 1 because EI is constant and the length are the same. So take note that there are no lateral translation because this is a brace frame. Okay, so no lateral translation for a brace frame, and the chord rotations B and CD as well are also 0. Therefore, your psi value, which represents your chord rotation for all members, is equivalent to 0, and your theta A and theta F are also equal to 0 since there is no joint rotation on the fixed support, which is the same as the case when we did our analysis on lateral loadings. Okay, so no rotation. Okay, so just remember the 2 theta I theta j minus 3 psi ij, but this time this will now be reduced to a much simpler formula, which is simply 2 theta I plus theta j without the need for considering the psi values because the psi for all the members are 0. In addition to that, which we have not done in our previous discussion on brace frame, is the consideration of your fixed end moment, which is due to the load, uniformly distributed load applied on beam CD and beams PE. So we need to compute for the FEM or the fixed end moment by way of using a very simple formula for a fixed ended beam, which is WL squared all over 12. Okay, so again, the rotation, the joint rotation is a negative counterclockwise and a positive clockwise there. Okay, so this negative, this is positive. Negative, positive, negative, positive. Hence, if we take summation of moment at each and every joint A, B, C, D, and E, where in here we cannot get anything out of it because we don't have any value here. So we can start from joint B, C, D, and E. We have to include the effect of your fixed end moment. So that's simply the one that will be added to your joint moments. Okay, so the moment equations are therefore as follows. So it will simply be equal to a value equivalent to 2 theta I, 2 theta A plus theta B. Okay, since theta A is 0, this becomes 0 plus theta B. So remember that the coefficient 2 is actually multiplied into the rotation, which has a subscript equivalent to the first, okay, letter here in your IJ node. So this is the near end, this is the far end. So this is a 2 theta A theta B, this is a 2 theta B theta A, but these are zeros. This is a 2 theta B theta C, this is a 2 theta B theta E. Okay, but this time since this is a beam, we have to add the FEM for all the beams. And as you can see, all those which have considerations of fixed end moment are all beam members. Okay, so if you want to do it manually, it's very easy. You just make use of 2 theta d theta c, 2 theta d theta e, okay, 2 theta e theta d. So the first subscript is always the one multiplied by the coefficient of 2. And the only difference again for the beam is that you add a fixed end moment. Okay, so this becomes a 2 theta e theta b, 2 theta e plus 0 because theta f is 0. And this is a 2 theta f theta e, and this is also a 0 because theta f is equal to 0. So in satisfying the equilibrium of moments, we simply get those values above, and taking the moments at each and every joint B, C, D, and E, we get equations 1, 2 to 4. Okay, in this regard. It is a good idea to arrange it, no? In terms of the chronological order of the joints B, C, D, E, but since this theta D is 0 here, we omit, of course, the theta D there and so on. So theta B, theta C, theta D, theta E is 0 here. Okay, so here theta C, theta D, theta B is 0 here. And here theta B, theta D, this theta C is 0 here. Okay, so these are now the 4 equations, and we can solve it readily. Summarize in here. Summarize in here are 4 equations with 4 unknowns, and of course using a tool, a matrix calculator, MathCAD calculator, in order to solve for these 4 equation 4 unknowns in terms of a matrix. We now consider the coefficients 6, 1, 0, 1, 1, 4, 1, 0. This is 0, 1, 4, 1, and 1, 0, 1, 6. Okay, so you call now this matrix of coefficient your stiffness matrix, which represents simply the matrix coefficient of your 4 equations above. Okay, these are the vectors of generalized displacement. Okay, they are generalized since sometimes you need to accord rotation. Okay, but in this case you don't have a chord rotation. But generally this must be a vector of generalized displacement. And these are now the constants, okay, the coefficients upon which your value of this will be derived or will be obtained. Okay, so these are simply the vector of moments or forces. Okay, so these are simply the vector of moments which comes from the fixed end moment that were obtained from the beam members. So this is equivalent to the mk delta in your stiffness procedure. Hence, the generalized displacements are therefore computed in terms of delta by simply taking the inverse of your matrix K multiplied by the forces or the constants. You get these values. Okay, so this is now your theta B, theta C, theta D, and theta E. Okay. So the generalized displacement corresponds to the degrees of freedom at the joint. So it simply refers to the DOF upon which the joint is free to rotate. Okay, that's why your theta A here, which is not a part of the matrix, and theta F is simply 0 and it's no longer included into your matrix expression since they are automatically equivalent to 0. So for the member end moments, we simply go back to the moment equations per member which were derived here on the basis of your uh, moment equations, okay, from the slope deflection equation. So this MAB will be paired, okay, to get your member moment. Okay, so this is the member BC and CB will be paired to get your member moment. Member EB and BE, okay, so these two here will be considered one member, and these two here, BC and CB, will be considered as another member, and so on. So all in all, we have 2, 4, 6, 8, 10, 12 moments, which corresponds to 6 members, as we are counting 6 members here. Member AB, which is 1, this is 2, then this is 3, 4, 5, and 6. Okay. So taking a look at the two equations now. This came from the moment equation per member MAB and MBA. So the matrix coefficient is actually 0, 1 with the theta A and theta B values. So the only difference with that of the embrace is this is a 2 by 3 matrix and this is a 3 by 1 matrix. So this time it's a 2 by 2 and a 2 by 1 matrix, such as if we do decompose it, your answer will be a 2 by 1 matrix there, and this is also a 2 by 1 matrix here. Okay. So for the computation of your members moments, we have to include for all the beams again an inclusion of your fixed end moment must be there, because this will only be due to end rotations without the consideration of your applied moments coming from the loads. So all the beams like members B and CD will actually constitute an FEM as an added moment to your end rotation moments. That's why we'll come up with your final moments here. But since these are no longer beams, these are columns D, E, E, F, just like columns A, B, and B, C. So you don't need to add an FEM since there are no member loads on A, B, B, C, D, E, and E, F. Okay, so that concludes your procedure on how to deal with the member moments or member forces using slope deflection method applied to brace frames with the help of a MathCAD tool. Thank you very much for listening. Have a nice day. I'll see you in the next video.